Okay, so this is going to be an update video on the Harmonic drive and the progress that I've made on it. So if you see here, the Harmonic drive is directly attached to the or the arm. So I have this piece of aluminum. This is Imperial, I believe, 1 inch by 2 inch architectural 6063 aluminum. So it's just C channel. It's actually surprisingly light considering how long it is. So I brought 3 of these lengths. So each of them is 3 feet long. I'm not expecting to use all of the aluminum on this arm. I just felt that having more is better than having too little. And I believe each of these pieces was about like $4 online. So it wasn't that big of an expense. But if we take a closer look at the drive itself, you can see that it is now integrated into the arm. So this was kind of like the drive before. It just had the motor mount attached to the actual drive itself. But I added this little piece on the end, and it has 8 bolts going through it, which kind of holds it all together. From what I can tell, it's super rigid, so it won't be going anywhere. And this just allows a direct actuation of the arm, so I don't have to work with belts. I have a Cad Design, which I'll probably put later in this video, which shows the full kind of mock-up thing. It functions just as the previous drive did, so you spin the input gear, and the output gear spins, obviously. Okay, so now that the drive is apart, you can definitely see the differences between the previous one. So in this one, there are 8 bearing stacks going around, and those are printed to be in an elliptical shape. So no matter the torques that the harmonic drive is under, the belt will always be in the same like ellipse shape. Previously, if you put it under torque, sometimes the ring, this little ring belt here, would deform, and I believe that's what caused the slipping of the belt within the harmonic drive rather than the motor just stalling out. So this is the previous strain wave generator to it. They're very similar, except as you see, this one only has 6 teeth, or 6 kind of mounting holes, while this one has 8. One of the big differences is I used this as kind of like a measuring tool to figure out the proper tolerance that I needed for the outer bearing. So here, previously, I only had 2 bearing stacks, so 1 bearing stack here and 1 bearing stack here, and each of these cross members had a different offset. So I believe this one was 46.5 between centers, this one was 46, and this was 45.5. So knowing that, I figured that for my printer and how I made it, the 46.5 distance worked the best. So then I modified the file. So this distance here, that is that 46.5 millimeters center to center, and that just allows it to fit properly. So there's almost no gap there is no gap between the circular spline and the flex spline ring. And that just allows it to spin super freely. There's a little bit more friction due to the bearing spinning, but it's pretty much negligible when you have this gear and pulley system here. It doesn't really make that much of a difference. Okay, so now that everything's back together, I'm going to cut to a video of me showing you the full CAD design and kind of my philosophy behind wanting this integrated arm joint and drive system. Overall, I think it'll be a lot more elegant than the previous one, and the accuracy of this is going to be much higher just due to the gear reduction. Okay, so now that we are on the computer, you can kind of see my full vision of how this arm is going to work. So if you see here on one end, this whole thing right here, this is just the harmonic drive. So you obviously have the circular spline / arm mount here. This is going to be driven, it's going to directly drive this arm. And then we'll have another harmonic drive on this side of the arm, which is facing the same direction. So the inputs will be on the top, and the outputs will be on the bottom. So the output of this harmonic drive will directly drive the proximal arm, allowing that to rotate. And then on this side, on the previous design, if you can imagine, there was like where my mouse is going, there was like a piece of MDF, a 1-inch piece of MDF, which went all around this, and that kind of clamped everything together. But in this one, I'm doing kind of the opposite. So in here, there's just going to be a single piece of either MDF or aluminum or something, which will be used to clamp these two pieces together. And with those two pieces being clamped together, there will just be a single piece going out to the main Z assembly. The Z assembly is going to be a much smaller one than the previous design. And I believe that I could probably get a larger range of movement out of this one too, just because I'm not contending with motors and belts and things like that. And then for those curious, this is like the original harmonic drive. If you see here, I only had the single bearings on either side. This one worked very well, but I don't think it stood up to the torques very well when I did the torque test. So I made this design. It's a little bit beefier. So here you can see that I added some material here, unlike on this design, which was open. I added that because when I was testing, this piece here would flex up and down depending on how much load was applied to it and where this was in its rotation. And then if I take the flex spline off, you can still see the brass inserts and stuff, but that's all right. You can see how the belt is driven. So the belt, these are exact dimensions, or fairly exact for how it's actually made. So the distance between these two bearings is 46.5 millimeters. I don't remember what the distance between these two are. It doesn't really matter, but it just allows the belt to have a perfectly elliptical shape, and that gives you the maximal tooth engagement on either side. Right now it's not set up properly because it's hard to CAD that in, but on the actual version, the tooth engagement is almost perfect, and I'm really hopeful that this thing will work very well. I'll probably provide all of these CAD files on my Thingiverse, and then update you guys when I print out another harmonic drive, and hopefully have everything working, or at least have a proximal arm working and functioning.